Hello, my name is Mansi Sakarvadia. I'm a second-year PhD student at the University of Chicago, and today I'm presenting our group's work titled Memory Injections, Correcting Multi-Hop Reasoning Failures During Inference in Language Models. We're going to start with a problem statement. Language models struggle to reason. When presented with the prompt, the largest coral reef system in the world is located off the coast of, the language model GPT-2 small returns the wrong answer. It returns the Philippines. However, if you break that bigger prompt up into two smaller reasoning steps, the name of the largest coral reef is, it returns the correct answer, the Great Barrier Reef, and using that intermediate information, we complete the question, the Great Barrier Reef is located off the coast of, the language model returns the correct answer, Australia. This is curious, as it appears GPT-2 small actually contains the intermediate information about what the largest coral reef system is called in its model weights, and is able to answer the question correctly. However, when prompted with the larger, more complex reasoning question up front, it fails. In this paper, we're going to attempt to understand a model's behavioral differences on what we call multi versus single hop prompts. An example of a multi-hop prompt is, the largest coral reef system in the world is located off the coast of, we're expecting the answer, Australia. This prompt is multi-hop because the model would have to resolve what the name of the largest coral reef system in the world is in order to correctly determine where it is located. Its corresponding single hop prompt is the Great Barrier Reef is located off the coast of. This prompt is single hop because the entity is explicitly stated compared to the multi-hop prompt. Before we jump into the meat of how to reverse engineer the model's behavioral differences on multi versus single hop prompts, we wanted to include a quick note on datasets. We used two datasets in this work. One programmatically generated dataset, which we call 2Wiki Multi-Hop or 2WMH. Examples of prompt pairs in this are the country of citizenship of Jaap's bear is Dutch, and the country of citizenship of the director of Lily's marriage is Dutch. You might have noticed that the answer to these prompt pairs is grammatically inaccurate. Additionally, once again, this was a programmatically generated dataset and has not been checked by human reviewers, so it may additionally contain factual inaccuracies. To combat this, we supplement our analysis with a human-generated dataset that the authors wrote. We call this dataset HAND. Example of prompt pairs in this are George Washington fought in the Revolutionary War, the first president of the United States fought in the Revolutionary War. This dataset was checked for grammatical and factual accuracy by two external reviewers. We now return to our single versus multi-hop pair example. The Great Barrier Reef is located off the coast of versus the largest coral reef system in the world is located off the coast of. Our goal on this slide is to see if we can localize the model's behavioral difference between the single versus multi-hop prompt. We do this by applying the model's unembedding matrix directly to the cached outputs of individual attention heads in the model. In this example, we have localized a source of behavioral discrepancy on layer 9, attention head 8. Notice in the green box, we have tokens that have been decoded from head 8 for the single hop prompt. We have tokens like Australia and Australians with and without a space, which are very close to the answer we're actually expecting the model to output. On the other hand, the multi-hop prompt outputs tokens from that head like coral, reef, reefs, and Fiji, which are related to the prompt but not nearly as close to the answer we're expecting. Now that we have localized a source of behavioral discrepancy between the single and multi-hop prompts, we form a hypothesis. We hypothesize that the reason the model misbehaves on the multi-hop prompt is because it is not resolving that intermediate entity. It is not resolving the fact that the largest coral reef system is the Great Barrier Reef before it attempts to locate where it is. We test this hypothesis explicitly by attempting to provide a memory, or in this case, the Great Barrier Reef, as a hint directly to the model. We do this by using the transpose of the model's unembedding matrix to encode the tokens for the Great Barrier Reef into the model's hidden dimension, and then adding those tokens directly into the outputs of head 8 before those outputs are concatenated with the rest of the attention heads and added back into the residual stream of the model. We measure if this, what we call a memory injection, was successful for this specific prompt by measuring the accuracy or the probability of the expected next token, Australia. Before this memory injection, the probability of Australia was 0.047. After the memory injection, the probability of Australia went up to 0.136, which is a 189% increase. I will remind you that for the single hop prompt, Australia was already the #1 most probable token, so this is a significant increase. On this slide, we provide additional examples of memory injections. I want everyone to look at the first example in this table. The god of thunder is the son of. The answer is Odin. Before we inject any information, the probability of Odin out of the box is 0.84%. After we provide the model with an additional memory of Thor, because the god of thunder is Thor, the answer probability of Odin goes up to 3.3%, which is almost a 4x increase. The rest of these examples are very similar. What this allows us to conclude is that language models often fail to recall intermediate entities, and when we provide those entities explicitly, we see consistently an increase in model performance. Now, the open question remains, where in the model is it beneficial to inject information and at what magnitude? On this slide, we delve into one experiment for GPT-2 small on the handwritten dataset. What you're seeing in this heat map on the y-axis is the magnitude at which we injected a memory. We varied this from 1 to 15, and the layer at which, specifically the attention layer at which we injected that memory. GPT-2 small has 12 attention layers. Each cell in this heat map represents the average percent difference before and after a memory injection of the expected next token of a prompt in our dataset. That means anywhere you're seeing green, on average, the model benefited from memory injections on average across the entire dataset. So magnitudes around 3 to 4, layers 4 to 8, I would say are ideal candidates for memory injections, while magnitudes of 15 seem to be a little bit too high for all of the layers. On this slide, we share a brief overview of all of our curated memory injection experiments for both GPT-2 small and large across both the handwritten and 2WikiHelp multi-datasets. What you're seeing in each of these heat maps is that there's areas that are very green, indicating ideal locations for injections, and red, non-ideal locations for injections. The next open question we attempt to answer is, how relevant does the memory need to be to the prompt in order for it to have a positive effect on the model's percent difference before and after a memory injection on the expected next token probability? We do this by comparing the pink line, which has curated memory injections across layers of the model on the left and magnitudes of injection on the right, to memory injections that are drawn from various parts of speech, including nouns, words from the top 5,050 most popular words in English, verbs, conjunctions, adverbs, and adjectives. And what we see is consistently that the pink line representing the curated memory injections outperforms the other lines indicating memory injections that are randomly selected from other parts of speech. This tells us clearly that the memories we're injecting into the model's forward pass have to be related to the prompt and answer that we're expecting. We now zoom out and provide an overview of these random memory injection experiments across both our models, GPT-2 small and large, across both of our datasets, handwritten and 2Wiki multi-hop. What we see on the top row is us varying memory injections across the model layers, and on the bottom row, us varying the memory injections across various magnitudes. And as always on the y-axis, we represent the average percent difference pre and post memory injection. In every single one of these graphs, the pink line, or the curated memory injections, consistently outperforms all of the other lines, which represent random memory injections selected from various parts of speech. This indicates that the content of the memory injection, once again, must be related to the prompt we're acting on and the answer we're expecting. To begin to conclude our presentations, we find that language models consistently fail to recall entities in complex reasoning tasks. We also observe a consistent increase in model performance when we curate memory injections. We further investigate the ideal magnitude and location for these injections across 2 different models and 2 different datasets, and we observe that random memory injections do not work. Thus, further backing up that memories that we inject into the model are actually contributing to model success. In future work, we are very excited about automating memory selections from external knowledge sources such as knowledge graphs or vector databases, as currently we are limited to hand curating our memories. Additionally, we would like to explore the inverse of our work effectively, which would be erasing memories during model inference, as currently we're adding information to the inference pass. It would be cool to see if we could take away information as well. And lastly, we would like to continue extending our work by applying memory injections to additional model architectures and datasets. With that, we conclude this presentation. I'm happy to take questions at the email on the screen. Please feel free to contact with any ideas, and our group welcomes collaboration as well, so feel free to reach out.